Hello, welcome to Material Science lecture. So this is lesson 3 for module 3, in which in this lesson I will talk and discuss about diffusions in solid. So the textbook's definition of diffusion is the movement of molecules or atoms from an area of higher concentration to an area of lower concentration, continuing until equilibrium is reached. So one example of diffusion process is the spreading of the smell of perfume in the room. So let's say, for example, you spray a perfume at one corner of the room. Eventually, it spreads to the rest of the room. It is through diffusions. So another example is when you have a soda drink. So the soda drink will eventually go flat when you open the can. So the soda go flat through diffusion. So our air has a lower concentration of carbon dioxide if we compare to the drink itself. So the carbon dioxide molecules depart from the beverage, from the drinks, and spread into the air through diffusion's process. So in material science, diffusions refer to movement of molecules in solids. So the learning outcome for this lesson is by the end of this lesson, you should be able to understand how diffusions occur and what the driving force behind diffusion process. You should be able to understand Fick's law and what factor will determine the rate at which diffusions will occur. And also you should be able to understand the effect of microstructure on diffusion's process. So diffusion's process is a process of mass flow from one place to another on atomic or ionic molecular level. So in solid state, diffusion can be defined as the movement of atoms within atomic network by jumping from one side of atomic site to another side of the atomic site. So in order for there to be a net flow of atoms from one place to another, there must be a driving force. So this is what we're going to talk in this lecture, is that we are going to learn about this driving force that will initiate the diffusions process in solid. Before we go further and learn about diffusions, I want to put some context on why you should know about diffusion. So why we want to talk about diffusions. So here is a couple of examples that maybe one day I want to design a container that holds pressurized gas. If I want this gas to stay in the container, I should know how the gas can potentially diffuse through the solid. So another example is, you've probably heard about hydrogen embrittlement. So this is a huge problem in oil and gas pipeline. So if I have a metal and hydrogen atoms or hydrogen gas molecule diffuse into the pipe, they will make this pipe more brittle. So this will make this pipe more susceptible to failure. Therefore, I need to know about diffusion rate in this solid. So finally, this also, you've probably heard about carburizing before. So I could selectively increase the concentration of carbon on a surface of engine parts such as this sprocket here. So if I want to make this part harder because I want them to be more resistant to friction, let's say, so I could diffuse atoms of carbon that can interstitially locate themselves into the material's crystal structure. That surface of that sprocket can be harder and more susceptible to more resistance to friction. So the way I introduce these carbon atoms into this solid is through diffusion process. So that's some example why do we need to learn about diffusion. So before we can talk about mass transport of atoms from one region to another region, we need to talk about how do atoms inside a crystal structure can move from one atomic site to the other atomic site. So we learn all atoms in the material has their own lattice position. So in a crystal structure that is perfect, like what you see in this slide here, there's no defect in this crystal structure. Atom cannot move from one side to the other side. However, we also know that all atoms have their own thermal energy and they constantly vibrate in their stable position. So all of these atoms is vibrating, but they cannot move and change position from, let's say, this side to the other side because there's no space for them to move. But we also learned that in real materials, there's always going to be defects such as vacancy. So when there's vacancy, this will allow the atoms to move from one atomic site to the other. But for them to move from one side to the other, these atoms need to push the other atoms out of their way. So in their stable position, they cannot do this. They need an extra energy, which what we call as activation energy, for them to push the other atoms out of their way. To illustrate the idea of energy barrier, I will use an impurity atoms that we call as interstitial impurity atoms, which we've already learned from defects in solid. So interstitial impurity atoms sits in between the interstitial space of the crystal structure. So in that lattice unit cell, there will be an interstitial space where atom can reside themselves if their size is very, very small. So if we look at this illustration, and this is the height of energy barrier where this atom needs to push in order for it to push the other atoms in his way or in its way so that it can change to this position. So it needs an extra energy to push these two atoms out of its way. So in its stable position, this minima indicate stable atomic site. And this maxima indicate that the energy requires to move that atoms from one side to the other. And again, when they are in their stable position, they have their own thermal vibration. But for them to move from one side to the other, they need an activation energy for them to move. So this height of the barrier is known as the activation energy. If an atom has enough thermal energy, it can cross the barrier. So diffusion depends on temperature of the solid, because we know to increase this thermal energy of the atoms, we need to increase the temperature. We see now that how often diffusions happen is in a solid is depend on the temperature of the solid. At high temperature, it is more likely for an atom to gain enough energy to move from one side to the other side. Diffusion can occur by two different mechanisms, interstitial diffusion and substitutional diffusion. So if we have an impurity atom in otherwise perfect crystal, the atoms can sit either on the lattice itself, so that's what we call as substitutional mechanism of diffusion, or they are small enough that they can sit in the interstitial space between the host material atoms. So we will talk about these two mechanisms in the next few slides. Substitutional diffusions occur only when there's a vacancy inside the crystal structure. So the movement of atom from one side to another side is only allowed when there is a missing atom inside the crystal structure. So the adjacent atoms can now move from one side to another side, leaving another side of vacancy in the crystal structure where another atoms can move. So just to recap, vacancy is a missing atom in the crystal structure. So from here, you can see that this mechanism of diffusions is dependent on the amount of vacancy and also on the existence of the vacancy itself in the crystal structure. So the rate of diffusions depend on two factors, which is how easy the vacancy can be created or formed in the crystal structure, and also how easy for that atoms to move from one crystal atomic site to another atomic site. So this mechanism of diffusions is much slower than the interstitial diffusion, which we will look into now. In the case of interstitial diffusion, the diffusing atom is not on the lattice side, but on the interstitial space within the crystal structure. So this, in this diffusion mechanism, the diffusing atom is free to move from any adjacent interstitial unless it is already occupied. So the rate of diffusion is only dependent on how easy for an atom to move into an interstitial. So these atoms does not require a vacancy defect because the crystal, all of them has interstitial space. If the atoms has a size that can fit into that interstitial space, that atoms can easily be diffused into that materials if the size is appropriate to the size of the interstitial of the host materials. So since this diffusion mechanism does not require vacancy, it happens more rapidly than the substitutional diffusion. How does diffusions happen beyond an atomic scale? So beyond just one atom moving from one atomic site to the other atomic site. So as I've said earlier, diffusion is a net movement of anything, a mass movement, mass flow of particle, atoms or molecules from a higher concentration to a lower concentration region. So if let's say I have a very still water here, it's no movement of this water, and I put some coloring in the water, food coloring. So you can see at the beginning that the color is just concentrated in one region. But if you leave it for a while, even without stirring it, that whole volume of this water will fill with blue color. So what happened there is that the atoms has their own thermal vibration, and they will start to randomly move. And they will move from a region where the color is highly concentrated to a region where it's not highly concentrated. And eventually, it will only stop when everything has the same concentration of that color. So I'll show that later at the end of the lecture. Diffusion describes the net movement of molecules from a region of high concentration to low concentration. So if I have an atom A here that sits next to a stagnant fluid here. So in a region A, I have, in region 1, I have a high concentration of A atoms, and diffusion describes the movement of these atoms from one side where it exists in high concentration to a low concentration due to the kinetic energy of that atoms and due to their random movement in random directions. So the net diffusions of A will be from high concentration, which is region 1, to low concentration, which is region 2. Use Fick's first law to quantitatively examine how the concentration in material change. So if we consider here a crystal lattice with a lattice parameter lambda. So this crystal structure containing a number of impurity atom A inside a host material B. So the concentration of impurity atom A may not be constant over the whole crystal structure, as what you can see here. So in this case, there will be a concentration gradient across the crystal, which will act as a driving force for the diffusions of impurity atom from the area of high concentration to area low concentration. So what Flux did was Flux basically measured the number of particles crossing the area per time. So what he measured is what we call as the flux. So he measured the number of atoms A in this case, crossing to this area per unit time. So he actually come up with this equation. So this equation here, I written it wrongly in your notes. So please correct it. So he basically relates the number of atoms that pass through an area to the diffusion of coefficients of the component A, which is related to the temperature. So the diffusion of coefficient can be determined in experiment. And he related to the change in concentration over change in the position inside the crystal structure. So that is what we call as flux. And in the next slide, we will use this to solve some problem. Before we do that, I would like to talk a little bit about steady-state diffusion. So steady-state diffusion is a diffusion process that takes place at a constant rate. That is, once the process starts, the number of atoms crossing a given interface, which is the flux, is constant with time. So steady-state diffusion is a situation where the rate of diffusions into the system is equal to the rate of diffusion out of the system, such that there is no net accumulation or depletion of the diffusing species. So in this case, the flux is independent of time. So the diffusive flux, the number of atoms per unit area, crossing per unit area, is proportional to the existing concentration gradient. One example situation where you can use Fick's first law is, let's say, for example, in the future, you're going to work with a pharmaceutical company. You're working as an engineer in a pharmaceutical company, and you are asked to design the plastic foil to cover a product. So the product that you need to cover is a tablet that is highly sensitive to a certain concentration of oxygen. So you need to design this plastic product. So if, let's say, you have designed it and you have a certain thickness of that plastic product, so you want to know now, if I use this as the protection for this tablet, what is the concentration of oxygen that going to be inside this plastic foil, and will it going to spoil your product? So you can use Fick's first law to get this concentration of oxygen inside this product. So if we assume that the diffusions is going to be in a steady-state diffusion, and we know that diffusions is a spontaneous process. So since there is a temperature difference between the atmosphere and inside that plastic foil, there will be diffusions of atom through that plastic foil. So if I bring back that Fick's first law, so the Fick's first law equation is, so the flux here, which is the mass flow rate or the number of atoms that going through a surface area per time, is what we call as flux, and usually this is determined through experiment, is equals to the diffusion coefficients, which is changed depending on different different temperature, and this is also determined through experiment. So this equation can also be rewritten as this equation. So this the fixed first law, which is the flux, is equals to the diffusion coefficients times the change in concentration and the change in position. So in our case just then, we want to calculate the concentration of oxygen when we have the thickness of the foil as 0.15 millimeter at temperature 30 degree. What is going to be the concentration of the oxygen inside this foil? So we can easily calculate the concentration of oxygen in the atmosphere using ideal gas law. So we can calculate the concentration of oxygen outside. We know the position outside, the change in position will be from 0, which is x naught is equals to 0. So the concentration, the position where the concentration of oxygen is at the highest, which is the outside of that foil, and it will be the change will be at where the concentration of the oxygen will be the lowest, which is at inside of that plastic foil. So the x is equals the change in position will be 15 millimeter. So we can now determine what is the concentration of the oxygen inside using this fixed first law. So if we rewritten this equation, we can rewrite it to this equation here. So from here, the only unknown that we don't have is the concentration inside the inside this plastic foil. So this is a steady state diffusion. So there will be a constant concentration gradient. So the concentration gradient won't change. So through calculation, through the experiment, we can determine that this is the value for the flux and this is the value for the diffusion coefficients. And using ideal gas law, we can calculate what is the concentration of the oxygen outside. So ideal gas law stated that pressure times the volume equals to the number of substance times the ideal gas constant times the temperature. So if we rearrange that to get the concentration, so the concentration will be the number of substance or atoms or molecules divided by unit volume equals to pressure, which is only the partial pressure because only 20% of oxygen molecules is at the atmosphere. So that's only 20% of the total atmospheric pressure divided by the ideal gas constant times the temperature. So the temperature here is the 30 degree. And if we do that calculation, we will get that the concentration of the oxygen outside is equals to 7.94 mole per unit volume per meter cube. All right. So if we do our calculation using this equation here, now we can get that the using fixed first law, we can get that this is the concentration that is going to be inside this plastic foil at one time. And now you can make your judgment. If this tablet here is going to be spoiled with this amount of oxygen, so what you need to do is you can increase the thickness of this plastic foil. So that's how one example where you can use fixed first law. We can move on to non-steady state diffusion. So in steady state diffusion, we say that the rate of diffusion is independent of time, just depend on the position. So the concentration gradient is constant. So in non-steady state diffusion, it is going to be a little bit more complex. We're not going to learn this in depth, but we need to describe what does it mean. So in Fick's first law, we have eliminated time, and we said that our diffusions is only dependent on the position. But in the non-steady state diffusion, we need to put time into perspective as well. So the concentration of diffusing species is a function of both time and position. So this is what Fick's first law looks like. So remember that from calculus, when we have variable that is dependent on two other variables, we need to do partial derivative if we are talking about rates, which is the change with respect to time. So Fick's second law is saying that partial derivative of concentration with respect to time is equals to the diffusion coefficient multiplied by second derivative of concentration with respect to position. So with this formula, we incorporate time and position to calculate the concentration, and this is what we call as non-steady state diffusion. So let's use an example to explain this. So let's say if I have this aluminum bar here, and we want to diffuse copper atom inside this bar. So I have to make an assumption here that our assumption is that the first assumption is that the bar has a limited length. So we assume there is a pre-existing concentration of copper atom inside this bar. So this bar has a length of x naught to x infinity. So this bar is very long, and it has a concentration of copper atom inside it already. So, and that is denoted as C0. So since we said that we have predetermined length, we will say that this bar is infinite length for a simplicity of calculation. Outside the bar, I have a copper concentration equals to Cs at the position x0 here. So this concentration of the copper outside, which is the Cs at the surface of x0, is very, very large compared to the concentration inside that material, the pre-existing copper inside that aluminum bar. So if we left the copper on the surface of this aluminum bar, it will eventually diffuse into the aluminum bar. And if we look at the non-steady state diffusion formula of Fick's second law, how will that look like? So if we assume when the time is equals to 0, so this is the time equals to 0, we have high concentration of copper on the surface. So if you look at the red color here, that is the concentration at time 0, and this is the concentration at time equals to 0 inside the concentration of the copper inside the bar. My assumption is I will let the concentration of copper on the surface constant. So it means that I will supply copper atom all the time at this location of at x0. So I will keep the concentration of copper here constant. So there's no depletion of copper inside on the surface of x0. So over time, what will happen is that if you look at position x, your experimental data will look like this. So at time, if you look at position x1, which is a certain position from the X0 position in this aluminum bar. Over time, the concentration of copper at that position will be at T1 will be at that concentration. So you have that many copper atoms in the bar at that position. At time 2, you will have a little bit more, and at time 3, you will have a little bit more. So this is the non-steady state diffusion. So the concentration of that atoms that you diffuse inside the materials will change over time. So that is the example of non-steady state diffusion. So your experimental data will look like this. So this is a microstructure of a steel that has gone through a case hardening process. So in this process, carbon atoms were diffused to a steel product in a non-steady state manner, creating a concentration gradient. So in non-steady state diffusion, more and more of this carbon atom will fill the steel product. So we'll feel if it has a length of certain length, more and more atoms will fill the bar. And so you can see that there are net accumulation or depletion of diffusing species, and this is dependent on time. Microstructure can also affect how atoms diffuse into materials. So if a polycrystalline materials has contain grains, so we know polycrystalline material has different grains. So the grain boundary in these materials will act as a diffusion pathway along which diffusion is faster than the bulk materials. The atoms diffuse through the grain boundary at a faster rate due to the disruption in the lattice, which provide a greater vacancy concentration. So you can see through this animation, through the grain boundary, the atoms can diffuse at a faster rate compared to the diffusion of the atoms through the grain itself. In summary, through this lecture, we learned that diffusions involve net movement of atoms or molecule from region of high concentration to low concentration. We've also talked a little bit about fixed first and second law and how we can use this fixed first law to qualitatively determine the change of concentration in materials. And we learned that grain boundary provides a greater vacancy concentration where diffusion happens at much higher rate. So that's about it for this lecture. So we finished with module 3. And in the next lecture, we will talk about dislocation, more about dislocation and how dislocation motion will influence plastic deformation inside the materials. So I'll see you in the next lecture.